So we start this morning with Francesca Carocci from Lausanne, who's going to tell us about a logarithmic approach to linear series.
Thank you, Richard, for the introduction, and thank you all for being here. So this morning I want to tell you about a joint work in progress with Luca, Battistella, and Jonathan Weiss, where we propose a way to study a linear series on nodal curves using logarithmic and tropical techniques. So for smooth curve, this is really a classical story. If C is a smooth projective connected curve, then a rank-R degree D linear series, or a GRD, is something we all know, is a degree D line bundle on the curve and a subspace of the space of global section of dimension R+1. And this is a very classical result that the modular space of GRD is projective, and if we take is a result of Gieseker and Petri that if C is general in the modular space, then this is actually smooth of the expected dimension. This has an expected dimension because this modular space is cut out as a degeneracy locus inside the Grassmannian over the Picard space, so it's really something we understand really well. And the question we would like to address is, how does this data degenerate when our curve becomes nodal? So how does the line bundle degenerate? How does the vector space degenerate? And what can we say about the modular space in this case? And of course, there are many ways to try and approach this question. For example, we could choose a basis for our vector space. Then we really get a map out of this data. And then the most natural thing to do is to consider quasi-maps or stable maps as a compactification. But when we do that, what happens if we think about quasi-maps or or stable maps limit is that usually not all of the components of my nodal curve C0 play the same role. For example, the map will contract some of them, and the degree could be concentrated on just one. And instead, we would like to have a bit of a more egalitarian compactification, where all the components of my nodal curve have the same rights, a bit like it happened in the case of admissible coverts, where each component has its own P1 to map to. And there is, for C0, a curve of compact type, the also now classical theory of limit linear series, introduced by Eisenbud and Harris at the end of the 80s, and then review from a more module-theoretic perspective by Ossermann, gives a satisfactory answer to this problem. And what we want to do is try to extend this type of result behind compact type using logarithmic techniques. Even though, in fact, all the... Yes?
Could you remind us what compact type is?
Yes, it just, you can think of it, there are two ways to say that. One way is that if I take the dual graph, this is a tree. But the important thing about compact type is that if I take the Picard of a fixed multi-degree, this is compact, it's proper. It's just the product of the Picard of the single components.
Ah, yeah.
So we see that this is of course is going to be important if you are trying to degenerate vector space and line bundle, because at least in wanting to degenerate a line bundle, we are already in business because these limits will exist. Having uniqueness then is another problem, and we will discuss that. And I should say that even for curves not of compact type, so we should think that going beyond compact type means that when we look at the dual graph, this dual graph acquires loop, so it has some genus, and so it becomes more difficult because the dual graph has some actual geometry. And there is some work in this direction, more recent, by Ossermann themselves, by Jensen and Payne, purely in the tropical world, and by Amini and Stevens, using more classical theory of compactified Jacobians and Voronoi tilings. And it's definitely interesting to try, it will be interesting to try and compare all of these different approaches and see what works best in what theory. But that's not what we're going to do today. So as I said, I want to take the logarithmic geometry approach, and so where does log geometry comes in? Well, if you hang in certain crowds, every time that you see a smooth curve degenerate to another one, you think, ha, this is really where log geometry is going to come in handy to tell me how to study the generations of objects. So let me just remind you quickly, if you don't already know, what do I mean by log scheme? This is not something this is something in the end we can think of in fairly simple terms. In fact, it's just the data of an honest scheme plus a sheaf of monoid, which comes with a map to the structure sheaf, which respects the monoidal structure. And we ask that the invertibles in the monoid are precisely the invertibles in OX. The way you should think about the sheaf is that it's selecting certain special function inside my structure sheaf that we want to elect to play the role of monomials, that we want to think as monomials. So since the invertible inside this sheaf of monoid are always just O star, many times we will simply look at the characteristic sheaf, which is the quotient, and so many times when I have to tell you how some log structure look like, what I'm actually going to describe is the characteristic sheaf rather than MX itself. And I will do two examples, which are the only one we need today. So the example 1, or 0, is the following. If we have X, which is your favorite toric variety, then we take this sheaf Mx to be the sheaf of function, which is invertible away from the toric boundary. And if we think about what this is on some affine toric charts, well, this is just really the toric monoid. So this is really what we usually call monomials in even in classical, in classical toric geometry. And the second example is going to do, the first part is actually comes pretty easily from this one, although it's already extremely interesting, and is the following. Let's take B to be the space of stable curves of genus G, and let's take D to be the divisor of nodal curves inside B. Then we consider this sheaf of monoids defined this way. These are the function, the regular function f, which are invertible away from the boundary of Mg. So actually the definition is pretty similar to the one we gave before, except that now this is not a toric boundary. But still, we have some normal crossing divisor, and we look at this function which are invertible away from there. And now let's think about how these, what are these monomials? What are these functions we are calling monomials? If we look at a point at our modular space, and the interesting things happen if we choose a point which is on the boundary divisor, then the divisor there is going to be cut out by what? By essentially the smoothing parameter of the nodes of the corresponding curve. So it's just the this divisor is just given by an explicit equation, which is product of the smoothing parameter equal to 0. And that is what we are calling monomials in this case. And so if we look at what is the stalk of this characteristic sheaf, well, if we take a point which is in the smooth locus, there our curve is smooth, and the invertible function away from the divisor are just the invertible function, so the characteristic monoid is 0. And instead, if we take a point which is on the boundary, what we see is that the stalk is given by n to the number of nodes of the curve parameterized by this point, which are precisely the number of smoothing parameter at this point. And what we want to do now is to, which is really a new example, is that we want to endow the universal curve itself with the log structure in such a way that the usual universal map has the right to be called a map in this category of log schemes. And the way we do that is the following. There is a natural log structure to be considered on these nodal curves, and it looks like this. If we have at a point of a nodal curve, and I'm looking at curves which lives over the boundary because nothing happens for smooth curves, then at a smooth point, the log structure is just going to be the pullback of the one from the base. So there are no new monomials. And what happens at a node is that we have two more generator, which once you correspond to the two local equations of the branches at the node, which have to satisfy one relation, which is just, if you think about this is just the shadow of the smoothing equation of the curve around this node. And if we consider this log structure, then our map pi is going to be logarithmic. The way you should think of it is that what it means is that monomials pull back to monomials under this map. So locally look like a toroidal map or a toric map. And it is log smooth, which I'm not going to say what it means, but the way you should think is that, again, locally, it looks like a dominant toric morphism. Yes?
If you take the universal curve, the model of the universal curve to be MG1 bar, is this just the log structure associated with the boundary divisor?
Yeah, where you have to consider also log structure on the markings, which I haven't, also markings can be given a log structure.
Okay.
Yeah. That's actually the clean way to say it, but you also have to take some log structure on these markings, and then that's precisely that. Thanks. Okay, and so these log structure are also defined in such a way that they can be pulled back, and so we are free to consider log curves over a point, just that the point comes decorated with some choice of monoid, and we can use this monoid to somehow remember in the log structure of the node something about a smoothing family. So we kind of record the order that a smoothing parameter wanted to have in a smoothing family. And so now, one advantage of using log structure is that it can give us some combinatorial structure we can work with. So given a logarithmic curve, we can associate a combinatorial object, usually called a tropical curve. But I want to think about tropicalization in a bit of a maybe not fully conventional way, so I'm going to tell you what I mean by tropicalization in this setting. In fact, I really want to make this tropical object become a geometric object. It wants to become an Artin-Fan, so it wants to become an algebraic stack, but an easy one. And I really want to have a map from my logarithmic curve to this tropical object. And I'm going to define it in the example of the easiest logarithmic curve, and that's really the only thing one needs to understand, because that is the local description, and all the rest is just done by gluing. So the easiest logarithmic curve is the one where I have just two components, and the base, the log structure of the base, is just given by the monoid n. And this algebraic stack I want to map to, that I keep saying is really a combinatorial object, is something super simple. I just take a nodal rational curve, and I quotient by the action of Gm acting with opposite weight on x and y. So it's just two copies of A1 mod Gm attached by their close point. How is this a combinatorial object? Well, this stack is really something simple. It has 3 points. It has 2 generic points corresponding to the x orbit and the y orbit, and 1 close point corresponding to the origin, to which both specialize. So if I were to graphically draw it, what I will draw is just an edge. Not just that, actually this stack, well, I mean, in the end it's just another curve quotient by some action, so it comes with its own log structure, which is again the usual log structure on nodal curves. So it's the one which is pulled back by the multiplication map from A2 to A1. I mean, descent in this case from the log structure from A2 to A1. So this, if I think of it in combinatorial terms, this is actually metrized by an element in the monoid, and so has the right to be called a tropical curve in the more usual sense, and then you shouldn't be too upset that I decided to call this map tau tropicalization. Well, but I have to tell you what this map tau is, and I have to convince you that this really comes naturally from the log structure. But so we have to give a map to these two copies of A1 mod GM attached from this BGM. What does this mean? This means that I have to give you two line bundles and section on the two components of the curve, such that when they restrict to the node, which is where this section is 0, these two line bundles are isomorphic. Or to be more precise, one is isomorphic to the dual of the other because the action has opposite weight. And where these two line bundles come from? Let's go back to this sequence, which comes from the log structure, and let's look at it. For each section or local section of the characteristic monoid, if we try to lift, if we see what is the set of lifts of this section to a section of the actual sheaf of monoids, this emits an action of O star, so is a O star torsor, which is what we usually think of as a line bundle. This is a line bundle. And what are the two sections we look at in this case? We look at these two sections E and F, which were corresponding to the local generator of the branches. And these are the two line bundles which are which I get if I look at the lifts of this section to a section of the structure sheaf. When I restrict them to each component, this is something very simple. It's just giving me a line bundle, which is the line bundle O of Q, and its natural section. And this relation, which they have to satisfy, precisely tells me delta Q is a parameter on the base, which means that the corresponding line bundle comes from the base, which is just a point for me. So what this relation is telling me is precisely that when I restrict to the node, these line bundles are isomorphic. And that's how I get my tropicalization map. And this is all very natural, so it can be glue over base for all type of tropical curve you will like to take. But in the end, let's keep in mind this one example, because this is really the one which makes us understand something. Okay, and at this point, I'm ready to give you the definition of logarithmic linear series. And I apologize in advance, because this definition is a bit of a mouthful, really. It's quite complicated. But again, if you have seen before one of the definitions of linear series in the Ossermann setting or in the Jensen and Payne setting, in any one of them, he always has a bit this issue. So maybe this is actually a feature of linear series rather than our fault. Okay. So the definition is the following. If we have a family of log curves, so locally we can think what we just did before, then the space of GRD is a stack over log schemes rather than over schemes, parameterizing the following data. At the grid D logarithmic line bundle, I'll say more later of what it is, but in first approximation is just a torsor under this group rather than under O star. A homotopy vector bundle on the tropical curve, which is also a torsor under a bit of a funny group. We're going to say more later about what it is. But in first approximation, if you forget this homotopy, you can think this is a vector bundle on the tropical curve. We are thinking of our tropical curve as this stacky object. So let's think back at the edge what this means. Well, we are looking at a toric stack. So a vector bundle is going to be an equivariant vector bundle on this toric stack. and a morphism on the actual curve from the pullback of the vector bundle to the log line bundle. And moreover, we ask our data to satisfy certain condition. We ask that there is a natural morphism by adjunction from E to the push forward of L to the tropical curve, and we want this to be universally injective. We want that the ramification of our linear series is only supported at smooth points. So I'll say later what does this condition for the vector bundle mean, and then we ask some stability condition for our ramification. Namely, we ask that every semi-stable component supports at least an inflection point. Let me stop for a second and let me make a few comments. First of all, sanity check. Let us notice that if we have a family of smooth curve, this is the usual definition of linear series. In fact, in this case, if I have a smooth curve, this sheaf is just O star, so I just gave you a line bundle. Gamma is a point, so I just gave you actually a vector space. A vector bundle on a point of rank r plus 1 is going to be just a vector space. And this is a linear series in the usual sense. The non-degeneracy is the usual condition. We want that our linear series, also if you're doing in family, is a vector subbundle of the space of global section. And all the other conditions actually do not arise in the smooth case.
Can I ask?
Sure.
So the tau, so the map tau from the curve to the graph, its fibers look like non-compact curves.
They are non-compact curves.
So the tau lower star is
it's not a vector bundle. It's horrible. It's like infinite dimensional. Yeah. Nonetheless, it makes sense to ask for this question. And the point is like universal injectivity means that I can restrict to whatever I want and it's still injective. And then you start seeing information there.
So that map becomes proper if you pass to like Berkovich space? Can you use that somehow?
You should tell me that. You can tell me later like how to do that. Yeah, but already like this, it tells me something, right? For example, already if I restrict to the edges, then this tau star L restricted to edges is I'm just looking at a graded vector space. And what this map being injective means is that I want that this equivariant vector bundle has all distinct weights. So, yeah.
Sorry, I got a little lost. What was tau again?
So tau is this map which goes from, I have my log curve, and tau is this thing that I call tropicalization, which is this A1 mod GM union VGM A1 mod GM. Yeah, and another comment, two more comment I want to make is that this condition that we want that there is no ramification at the nodes, this is very much in the spirit of log Gromov-Witten theory with expansion. So we do not want anything bad to happen at the nodes. And I'll come back to that, but I wanted to say that this condition about this realizability condition, whatever it is, if I don't tell you, ask me at the end, this is only relevant outside compact type. So this is, yes?
In your compact type case, in Eisenbud-Harris, you had many vector spaces.
Yes. You know, in fact, I don't have a line bundle, and I don't have one vector space. I have this logarithmic line bundle. You know, when I have a logarithmic line bundle, the logarithmic line bundle is the data of many vector spaces, of many line bundles. We're going to see that in a second, once I tell you what is a logarithmic line bundle. That's right. There is a notion of aspects, and they will have to pop up also here. Any other question? Okay. So, for obvious reason, I will essentially spend probably the rest of my time trying to explain all of these words that I say and try to convince you that they are more natural than they sound at first. So before starting my explanation, let me tell you what is that we can prove about this linear series. So what we can prove is that this moduli space, it's admits log smooth cover by logarithmic schemes. So it's not really representable in the sense of algebraic stacks, because an algebraic stack will have to have a smooth cover, and instead this log smooth cover means that I am allowed to take subdivision. But not worry too much about that. You can ask me later if you're interested in what it means. And what we can prove is also that this is proper over the base, meaning it satisfies a evaluative criterion. And it has a perfect abstraction theory relative to irreducible stack. And in particular, what this means is that it has a virtual class of the expected dimension relative to the base, and we get essentially for free a regeneration theorem. So, which means that if we have a point in this modular space that has the expected relative dimension at a point, this is actually smoothable. It actually lies in the closure of linear series on smooth curves. And I'll make a comment before starting the explaining further, which is the failure of the representability comes from these log line bundles. This is the stack which is not representable. This is really where the problem is. And maybe one way to think about this, one first way to think about this log peak, hopefully I'll give you more point of view, is that this wants to be a minimal toroidal compactification of the Jacobian. Except that this minimal toroidal compactification does not live in the world of schemes, but rather in this world of log schemes. But every time that we choose, for example, in stability condition, maybe the Caporazzo stability condition, and we get a toroidal compactification, this gives us a representable model of our log peak. So all of the usual compactification we know and love, they all map to this log peak. So we should think that they're all birational over this log peak. So
is this realizability condition, is it intrinsic or is it defined by a closure?
The one for the vector bundle. Yeah, this is unfortunately defined by a closure. That is what makes us the most unhappy. Yeah. So I've been saying log line bundle a lot, so let's try and say a bit more of what these objects are. So what we already said is that this is some torsor under this logarithmic multiplicative group, and not just that, but we also have to ask a further technical condition, but which I'm not going to explain, but I'm just going to say that this is needed to make sure that at least all deformations of this object are algebraizable, so things which are not too weird happen. But let me try, I would like to justify why we need to define, why are log line bundles defined this way, and why this is not such a strange definition. And to do that, I want to tell you what happens in one parameter family. I want to tell you that this is really the right way, this is really a natural way to define limits of line bundle. So let's take a one parameter family. So a smooth curve degenerating to nodal 1. And let's start with some degree D line bundle on the central fiber. Now there are two ways we can think about this degree line bundle, either as the data of its transition function, or maybe as we can choose a divisor representing this line bundle. Then we want to try and extend this to an object over the whole family. And however we see it, things do not go quite right. Because if we try to glue with this transition function, extending this transition function, there might be zeros and poles along the central fiber, so we do not actually get a line bundle. And if we try to take the closure of this divisor, what usually will happen is that we'll get some honest divisor intersecting the central fiber in smooth points, but also some vertical components, and maybe some points ended up at the node. The fact that there is going to be some vertical components is what causes limits not to be unique. And the fact that some points can end up at the nodes is what causes limits not to exist at all as line bundles. But then, maybe one thing that we can try to do is think, well, let's allow this transition function to have these zeros and poles along C0. And this is precisely what this group does. These are precisely this MC group. What are these? These are functions which are allowed to have zeros and poles along C0. It's just that we are keeping track of the order of the pole and of the leading term. So if we allow this more general transition function, limits exist. But not just that, we also get another advantage, even in the compact type case, where limits always existed, namely that if we, these logarithmic line bundles, so which are classified by the H1 in the H1 cohomology of this sheaf, if we take a line bundle and a twist of this line bundle by a vertical divisor, they actually represent the same class as a log line bundle. So we killed two birds with one stone. And the second thing is not too hard to explain. Our favorite sequence came back, which is this one. And let us look at the associated long exact sequence in cohomology. So we have a sequence like that. And what we can see then is that, so we have a map from the section of the characteristic sheaf. We saw before how to associate to a section of the characteristic sheaf line bundle. And if we have two line bundles that differ by a line bundle that comes from one of these sections, these are going to be the same in the quotient. But what is this? What are these sections? Well, this I'm not gonna explain. I'm just gonna tell you. But if you go and unravel what is this, what does it mean to give a section of this characteristic sheaf, you realize that this is equivalent to give a piecewise linear function on this tropical curve. Now you have to, this one you always have to have two pictures in mind. The actual combinatorial object and this stacky object. Ah, yes. So gamma is two people at once. And these are really the category of these artinfants and the category of these cone complexes is really the same on a precise level. So there is really a functor going back and forth between these 2 points of view. So I was saying, if you go and unravel what it means to give a section of this characteristic sheaf, you realize that this is really the same as giving you a conewise linear function from this tropical curve to the real number. So it's just this is just a function which is linear on each edge, but possibly with different slopes. And like in toric geometry, so you should think of this as the fun of this object. As in toric geometry, to each of these functions correspond a line bundle, which I can now pull back. And these line bundles that I obtain this way are precisely the vertical twist. So that's how I can see that two limits that differ by a twist, they are the same.
So I apologize for backing you up, but can I ask a question about the previous the page where you were showing the example degeneration?
Yeah.
This guy, yeah. So my understanding is that in these stacks, the base schemes also have log structures. So,
yes.
So in this example, you have the log structure there, and what role does that play? Why were you forced to have log structures on the base scheme?
Because I want this curve to always be log smooth, and then forces to have some log structure on the base if there are nodes in the fiber.
The curve is log smooth, even.
Yeah. Yeah. In order to have for this to be a log smooth curve, I have to put some log structure, which is just the usual toric log structure of A1 at 0. Yeah.
I thought that you can always extend a line bundle if the total family is smooth.
That is true. If the total family is smooth, you can always extend the line bundle. But no, I'm not under this assumption. Yeah. More questions? Okay. So there is another way I want you. I mentioned before this bounded monodromy, and I want to give another way to think about it, and maybe another way to think about this log peak. So again, everything goes around this sequence. Every time that we have one of these log line bundle, we can associate it. We can look at the associated torsor under the characteristic sheaf, just quotient by the action of C star. If this is trivial, so if this has some section, then what this means is that there exists some actual line bundle which represent my log line bundle. And what the bounded monodromy condition tells me is that for any family of log curve, after you performing some log blow up on both the base and the fiber, this is possible. So what this condition means, it means that on some model of my curve, some refined model of my curve, where I might have blown up some nodes, it's always true that there exists a line bundle that represents my log line bundle. So maybe one way, a more like, let's say, extrinsic of expanded way to think about log peak is as the limit over all possible models of my curve of the Picard group modulo the action of the conwise linear function, which identify line bundle that differ by vertical twist. So to answer Alessia's question, a log line bundle contains the information of all of the aspects. If I look at all the line bundle which map to a given log line bundle, these are all the aspects of a usual limit linear series in compact case you are thinking about, because those are precisely twist one of the others, that how they arise. And indeed, notice that when C is compact type, in fact, in that case, in this case, I already have a line bundle representing my log line bundle on a given model, and then this log peak, well, is what? Is just peak quotient by this action of the twist. And what does this action of the twist mean? It means that I can fix my theory multi-degree and arrive there, and that is what my log peak is. So that's how it works. Okay, this was the first ingredient of was the first. What's going on? Ah, yeah, this was the first ingredient of our definition. The second ingredient was this other weird object, namely vector bundle aptiomoiety on the tropical curve. Let's remember that is always my tropical curve. So, if we think about what this MC group was, and we were defining this log-line bundle as torsor under this group, one way to think of it is that this is a compactification of the multiplicative group. So that is an extension of the multiplicative group. And what we consider here is we take the usual linear group, and what we do is we extend its center. And this is what this GL tilde is. And we consider torsor under this group, and that is what we call a non-motetti vector bundle. And again, let me explain exactly what this is. Let me try to give an intuition for what this is. As before, to one of this homothetic vector bundle, we can associate this torsor under the characteristic sheaf. And so now I can at least tell you what was the meaning of this morphism between these two objects in the definition of linear series. Well, to both the log-line bundle and this homothetic vector bundle, I can actually associate torsor under the characteristic sheaf. And this is the same for the curve, for the actual geometric curve, and for the tropicalization. In other words, this map is strict, which means that the characteristic sheaf are really, I can identify them. And then what this map means, it means that every time that I have a local section of this L bar, so of this torsor under the characteristic sheaf, so every time that I have a trivialization, this was the, let's remember we had peak, log peak, H1C MC bar group. So if I have some object in here which gives you a trivial object in here, it means that actually was coming from a line bundle. So every time I have this section, I actually can lift both this log line bundle and this homothetic vector bundle to an honest line bundle and an honest vector bundle, and I have a map between them. And this map between them has to satisfy some compatibility condition, namely that if I have another section, then the two given map just differ by the addition of this section. Okay, and let me tell you what this is on an edge, which is probably gonna hopefully clarify something, and is probably gonna explain also why this homothetic vector bundle come out naturally. And to tell you what it is on an edge, let me remind you a little bit of result about vector bundle on toric variety. Is we know from Kliatchko that a vector bundle on A1 mod GM, which just means an equivariant vector bundle on A1, is simply a zeta filter vector space, such that this filtration becomes, this vector space becomes 0 for very negative n, and becomes an isomorphism for very positive n, so it's exhaustive. Well, and now it follows immediately in this case that a vector bundle up to homothetic on A1 mod GM, we can also make sense of this on A1 mod GM, is just a zeta filter vector space up to shift. So A1 has its own log, A1 is a toric variety, has its own log structure, which is the toric log structure. But if we look at the H1, if we look at this cohomology, this is 0. And then since this cohomology is 0, it means that every vector bundle up to homothety actually is represented by an honest vector bundle. I'm just identifying those that differ by a shift. And now we can also see what are these vector bundle up to homothety on our edge, on our curve gamma. As before, let's first think about what is a vector bundle. Well, I have to give you two vector bundle on A1, and then I have to, which means two vector spaces, and then I have to give you an identification of this two vector bundle on the close point, on the BGM, which means I have to give you identification of the associated gradient. And let me just point out that since the action was with the opposite way on this 2A1, then the identification is also with the opposite sign. And okay, maybe I told you now what are homothety vector bundle, but I haven't. But I still have to convince you that it's something very natural. I really wanna tell you where they come from, and actually they come from somehow something very classical. They, in some sense, they were already there in the Eisenbud and Harris theory of limit linear series in the compact type case. Just that, yeah, it wasn't phrased this way. But somehow, if you wanted to try it and become modular the definition of Eisenbud-Harris, you would have come up with the definition of homothety vector bundle. So let me remind you what is the classical definition. If C is a curve of compact type, then a GRD on C is just the data of a honest GRD on a smooth curve on each of the irreducible component of my curve, which satisfy the following condition. If I have two components joined by a node, and then the following condition has to be satisfied. The vanishing sequences of the two linear series, the two components at the node, have to agree. So have to sum to the degree d. This is actually what Eisenbud and Harris they call a refined linear series. Usually, a linear series is called anything where the inequality is satisfied. Any question about that? So we have these two vector spaces of section, one on the component CB, one on the component CW. And if I look at what are the order of vanishing of this section at the point QE, I get an increasing sequence of R+1 distinct numbers. And then what I ask is that the vanishing sequences at the node of these two linear series agree in the following sense. Let's try and see what this means in our language. From these vanishing sequences, we get 5 filtrations of this vector space. The end piece of the filtration are just the section which vanish at order at most n. This gives me my increasing filtration. And then, if I now go and see what does the linear series condition means, it means the following. It means that when I look at the associated gradient of these two filtration defined by the order of vanishing on the component CB and on the component CW, they agree up to reversing the order and shifting by D. Now, let's remember that that we said before that a vector bundle on the edge is precisely the data of a vector bundle on the 2A1 of the normalization, together with the identifications at the node. And those in turns, they are nothing but a choice of filter vector spaces plus an identification of the associated gradient. And the fact that there is this shift by D, what this means is that I do not really have an identification of the two vector bundle, but I only have them after I twist my vector bundle by a suitable function on this edge. Here I'm denoting by gamma. The PR function which has log 1 along this edge. And what it means is that this isomorphism is this identification gives me a well-defined vector bundle only up to homothety. So a refined linear series is really the data of a vector bundle up to homothety on the tropical curve, and one can go the other way around. And this is pretty much all I wanted to say. Probably the last thing I wanted to do is some quick comment about the realizability of the vector bundle. I want to tell you what was, I didn't say what it means, I wanted to say what it means and where is the problem. So, for all this time, we have been talking about the edge, even though, as I said, this was the case already covered by Eisenbud and Harris. But the interesting stuff in this theory really happens when we have a tropicalization which has some genus. So, for example, when we have a loop. Now, what happens in this case? That let's think about just the data of what this vector bundle should be on this loop. Well, I will have to give you a vector bundle on each one of the two edges, and we discussed before what it is. And then I have to give you an identification at the two nodes. So I have to give some gluing there. The problem is that not all the vector bundle on this loop that I can write this way are necessarily a degeneration of a vector space. And the problem is that there is a cocycle condition to be satisfied for this vector bundle to actually come from a vector space, which is not visible if I just look at the loop. And this only becomes visible if I take the tropical curve and I look at it over a dBr. Then I have an extra point, the vertex of the cone, and then I really see this cocycle condition, but otherwise I do not. And what it means is that if I do not ask this realizability condition, not just my vector bundle are not necessarily do not smooth, but I will not even get an algebraic stack. So it's really something that I need to ask. And maybe I should say that we did everything for overlog peak, but there are situations where we can do something better. For example, if you are interested in the generation of canonical series, we do not need to look at log peak. So we choose our line bundle is the canonical line bundle, and then this theory will give us a proper compactification of the space of canonical linear series over mg bar. And I think that's something we would like to do is trying to understand what are the reducible components of this compactification and which one dominate mg bar. And yeah, I think that's all I wanted to say, so I'll stop here.
questions?
So this, so if I actually wanted to construct vector bundle on gamma up to homothetic, I mean, in the toric case, you can use this Bruhat-Tits building of GLN.
Yeah.
So what's the relationship with the realizability there?
If your vector bundle is realizable, it does come from the Bruhat-Tits building.
But conversely?
Conversely, you cannot. It's not clear how to map gamma into the Bruhat-Tits building unless you already have chosen a smoothing. The Bruhat-Tits building of what? If you're just on the central fiber, for example, and your central fiber is FP, you don't know whether you should try to smooth to p-adic or FPT, and these are two different buildings. So
the spherical versus
yeah.
the
So, but yeah.
So, but in the case R equals 1, do you recover the theory of admissible cover?
So the theory of admissible cover is going to be not quite this one, is going to be a blow up of this one. So we know how to get the theory of admissible cover, but this is not what I talk about today. But there is a way to recover. So one way to think about it is, let me put it this way. What this theory C is essentially in the theory of admissible cover, each component maps to its own P1, and then there is some compatibility at the nodes. In here, you just see each component mapping to its own P1, but without asking for the compatibility. So it's a more local theory. But there is a way to enforce that.
So if you want to count the number of GRD, go degenerating the curve to not the usual -0 and then rational case, maybe do some loops.
Yeah.
Can you do that using now this theory?
What do you mean counting?
I mean, if rho is 0.
If rho is 0. So actually, we haven't tried, but I think there are some results in this direction in the purely tropical setting already before then.
But it seems likely that if you do other degenerations, other than, I mean, the tropical people all like, they like this chain of loops degeneration.
Yes, the
if
tropical.
You do the other one, it'll be a purely virtual way to get.
Yes.
It'll need the virtual class.
Yes, that we haven't tried, but the tropical people always do this chain of loops, and that's the way they compute it. So, yeah, I don't know. It's we haven't tried. It's a very good question.
Okay, so there's no more questions. There's coffee outside in 1 minute 15 seconds, and then we meet back here in 31 minutes and 10 seconds.